Thank you. Good morning, everyone. I'm here to present the effect of a time-of-use feed-in tariff on optimal net zero energy home design. One of the things I think I've come to the realization is that likely you know as much about net zero energy home design as I know about quantum dots and molecular chromophores. So I'm going to really start off with the messages that I want to convey in this talk. So the first is that targeted incentives can affect solar optimized building design. And my second point is that you really want to consider building design from a holistic approach. And you would like to avoid sub-optimizing components and optimizing a building as a system. So in this case, you want to consider energy conservation in competition with energy generation. So some quick overviews of what I'm going to talk about today. So I'm just going to give you an introduction on what a net zero energy building is, why it's important in the relation to PV. The method, I'm attempting to sort of go over some of my PhD thesis and give you sort of a backbone on what you would need to do in order to repeat this analysis. And I'm going to talk about briefly some results, so what an optimal design looks like. And then I'm going to compare some paybacks for energy conservation versus energy generation. And I'm going to look at cash flow diagrams in a couple scenarios, followed by conclusions. So introduction, net zero energy buildings, they generate at least as much on-site renewable energy as they use over an annual period. And I guess the second question to that is, why would you ever want to do that? And the reasons why are buildings have an enormous stress on the primary energy use across the world. 40% of primary energy, 70% of electricity, and that's increasing. And looking at moving towards distributed energy platforms as a way of reducing peak grid loads, reducing blackouts, and then mitigating the need for future grid expansion. These buildings pay back in terms of embodied energy, and they can also be an attractive economic opportunity for building owners as well. So briefly, how do you achieve a net zero energy buildings? Well, the first thing you need to do is reduce your energy consumption, roughly by about 40%. You need to look at improving the mechanical efficiency of your equipment and integrating some control strategies that are beneficial. And then at that point, you start looking at renewable energy. And this is under present economic circumstances. This could change in the near future too, especially with the dropping price of PV. So if you're interested in looking at some case studies for outside of a home realm, then I suggest looking at one of the deliverables from the Task 40 Annex 52 that I'm part of on net zero energy buildings. And this looks at 300 different case studies across the world. So I just wanted to give a quick example of a near net zero energy house. This is the Ecoterra building. It's located in Eastman, Quebec. This was designed to reduce cost and not necessarily energy, so that's why it didn't achieve the net zero energy target at the time. If you could do a comparison to a typical building, you'll see that the Ecoterra uses approximately 1/5 of the net energy consumption. And this was a collaborative effort between a builder, Alouette Homes, as well as the research network I'm part of, and CMHC and NRCan. And one of the points I wanted to make is this building uses amorphous silicon. At the time, this was sort of the state-of-the-art technology for thin film. Now that's no longer the choice that you would make into this design. So if you were to choose 12% or 15% PV, this would be a net zero energy house without doubt. So it's just kind of showing how quickly the times change as well. So methodology. So one of the things that you need first is an energy model. You need to be able to model trade-offs between passive solar performance, daylighting analysis, looking at control strategies. You need to model occupant behavior and how people use appliances as well as their thermostats. And in addition to considering renewable energy generation. The tool I use to do these simulations is Energy Plus. I'm looking at an objective function of net energy consumption, so meaning that electricity consumption in lights, domestic hot water plug loads, as well as looking at heating consumption, cooling consumption, and then subtracting that by the energy that you would create in PV. So you would achieve a net zero energy building if this objective function is 0 or less than 0. So some of the variables you would want to look at, passive solar variables. Passive solar is sort of becoming an antiquated term at this point, but it really refers to the collection of solar energy without using a transport medium. So we're looking at using visible solar radiation in addition to ultraviolet and converting that into infrared through a glazing in a window. So this is an example of a building that I sort of modeled based on. So you'll see that this is the south-facing side. There's a large window-to-wall ratio, and then on the roof, this is a building integrated PVT system that was designed by my supervisor and co-students. And one point I wanted to make was the PV models. There's 3 models available in Energy Plus. Only 2 of them are really appropriate for this, and you need to have some temperature coupling. So this becomes a very big problem quickly. You can easily have 30 design terms. If you consider 6 to 10 discrete possibilities, your solution space goes up to 10 to the 30. So this explodes very quickly. The cost model, I'm using a life cycle analysis over 30 years. I'm looking at initial material and equipment costs from RS Means database. One thing that RS Means does horribly is PV costs, and I chose a very conservative cost for PV per watt, as well as the total installed cost. After this conference, I've realized maybe this is a little bit high, but let's just consider that this is a fairly conservative estimate of your PV equipment costs. I'm looking at the replacement costs, operational costs, and salvage costs of materials at the end of the life cycle. And then I'm also looking at revenue generated from renewable energy incentives, such as the FIT program. So incentives, I do look at feed-in tariffs, in this case, a time-of-use feed-in tariff. The rest of these aren't really important, so I'll skip forward. So the reference design, you have to compare a net zero energy building to something, and the reason is because your cost analysis would just become too complex, considering initial cost, sales, and commissioning. So I'm doing a marginal cost analysis on how much more it would cost than a typical building design in Canada. So to do this, I'm using energy codes to specify insulation values and some other factors, but I'm also using a database of energy collected through energy audits in Canada. This is a program that I represented for a little while, so I'm quite familiar with it. And it's excellent at deciphering typical window-to-wall ratios for homes, as well as envelope air tightness, which is not dictated by energy code. So a time-of-use feed-in tariff, why would this be interesting? And the idea is that you're creating revenue during peak periods of electricity demand. So one thing that I was anticipating is that in a holistic optimization analysis that there are certain factors that likely this would affect. So to show you the structure that's being used, this is modeled based on the present time of use billing in Ontario, where you pay more for electricity in the morning from 7-Eleven in the winter, and then less so during the day. And in the summer, you're paying mid rates in the morning, and then your peak rates typically happen in the afternoon. For this, I'm using the mid-peak rate, approximately the present OPA offering, which is 54.9 cents, and then sort of fractions of these for the peak and the off-peak rates. So throwing all this into sort of a pot and then optimizing it is also a task that you need to consider seriously. So I'm using computational evolution to accomplish this. This is an algorithm that I developed for this particular purpose in my PhD thesis. The development strategies is I'm looking to improve on results and to make it faster. So it's a typical engineering analysis that you want to get better results and get them quicker. Typical previous methodologies, we're using about 40 hours per optimization run. I've got that down to about 2 hours with better results. So this is a deliverable of my thesis. So let's get into results. One thing with the building is that the orientation of your solar collecting surfaces, so this is your PV as well as your window-to-wall ratios for your passive solar performance, is pointed slightly east. And the reason that this is happening is because in the winter you're going from a cold morning start into a typical heating set point because people want their house cooler during the evening to save energy, but then they want it warm as soon as they get up. So pointing it slightly east would actually decrease the heating load. And if you were to point this building slightly west, you would improve your revenue streams. However, you would have to have more cooling during the afternoon in order to avoid too much solar gains in the summer. So there's a trade-off analysis going on here. So if you look at the effect of using a time of use versus a fixed rate feed-in tariff, is that you increase revenue by about $1,000 per year. This is a 20% increase in revenue. And because passive solar performance doesn't really change that much if you orient slightly one way or the other, that you're getting approximately the same performance for the home. One thing I wanted to do, this was conversations with some people during this conference, is I wanted to also compare PV payback to some energy conservation measures. So in this case, I'm looking at a separate analysis. Just the PV with a feed-in tariff would have about an 11-year payback. This is a little bit high. You would expect it to be about 7 to 10, and it's because I have a fairly conservative estimate of PV costs. So let's compare these to some energy conservation measures. So for example, improving the air tightness of the envelope has about a 6-year payback going from a typical home. Looking at ceiling insulation and going from an R40 up to an R60 value has about a 10-year payback. And looking at, let's say, wall insulation going from about an R20 to about an R45 has about a 4-year payback. So all these have in common is that they're lower than your PV payback. So when you include all these together in an optimized building design, your energy conservation measures are pulling down your PV net costs. So this is sort of an interesting thing that you want to optimize based on the system levels, because that's actually beneficial to your total building design, that you're actually reducing the cost of PV payback in this case. So cash flow diagrams. At the top, I'm looking at the optimal net zero energy design. It has a higher initial cost but a lower operational cost, and you'll see at some points that there is equipment that's being replaced. For the reference building, it has a lower initial cost but higher operational costs, and then the difference between those two is shown by this diagram. And then if you do a cumulative sum, so if moving forward sum of each of these cost flows, that you would achieve a payback around 9 years. So this is using the time of use feed-in tariffs. And I want to consider a couple scenarios quickly. So what if electricity instead was 14 cents per kilowatt hour instead of 10 cents that I used? Your payback goes down to about 7 years in this case. And moving on to the next scenario, what if this dollar per watt target that everybody's talking about was a reality? And this is, in my opinion, sort of a sign of a very disruptive technology, because your payback goes down to 3 years. And in this case, we have an inversion that the PV savings are actually helping to pay off the energy conservation measures in your home. I just find that to be a very interesting interplay between the two. So conclusion, a net zero energy home is economically attractive. It's a long-term investment presently. You're looking at about a 10-year payback with PV at $6 per watt, with a feed-in tariff, of course. But that payback would go down significantly, assuming that the feed-in tariff stays the same and your price per PV would be going down. There's some system-level design strategies going on here. You're actually leveraging energy efficiency measures to reduce the PV payback by 2 years. And in the future, it's possible that PV incentives and PV-generated electricity might actually aid in improving energy conservation measures in net zero energy building design. So in the example, improving your ceiling insulation from R40 to R60 is actually a poorer decision than installing PV on your roof, which I think is quite revolutionary. So incentives, they do influence optimal home design, and a time of use feed-in tariff can reduce peak loads while improving revenue if it was employed. So this is more of a hypothetical analysis. So I'd like to thank you for your attention, and please, if you have any questions, feel free to ask me or by email too.